Hello everyone, welcome back to the online tutorial on quantum chemistry. In the last video, we went through the Bohr atom model and we found that Bohr atom model was a stable model of atom. And the key concept of the Bohr model of atom was the quantized angular momentum. Bohr assumed that the angular momentum is quantized. Angular momentum of the electron, mvr, is equal to the integral multiple of h divided by 2 pi, that is nh divided by 2 pi, where n is 1, 2, 3, etc. So bringing this angular momentum quantization, Bohr was able to calculate the allowed radii of the orbits in the hydrogen atom, and the radius of the nth orbit in the hydrogen atom was calculated to be epsilon 0 n square h square divided by pi m e square. It means that the radii of the orbits in the hydrogen atom are quantized. It cannot have all values of the radius, but it can have only certain discrete values of radius. And also, Bohr was able to calculate the quantized energy levels. The energy of the nth orbit En was calculated to be equal to minus m e raised to 4 divided by 8 epsilon 0 n square h square, which again shows that the energies of the orbits are also quantized. And as a big success of the Bohr theory, an expression for the Rydberg constant was introduced. The Rydberg constant was derived to be m e raised to 4 divided by 8 epsilon 0 square ch cube, and the value was calculated to be 109736 centimeter inverse, and this is the calculated value from the Bohr model, and the experimental value is 109677 centimeter inverse. You can see that the calculated value and the experimental value are very close. So Bohr model was very much able to give a theoretical explanation for the Rydberg formula. This was a major triumph in the history of quantum theory, because Rydberg formula was an empirical formula, but it was able to explain the frequencies in the hydrogen emission spectrum. But Bohr model came with a theoretical explanation to the Rydberg formula. And we found that the values calculated for the Rydberg constant, they are very close to each other, but still, is it possible to refine Bohr model to reach an even better value for the Rydberg constant? For this, let me try to introduce a certain basic or practical principles of physics. I have a chopstick, and we know that chopstick has a thick end and a thin end. I want to balance this chopstick over my finger. When I try to balance the chopstick at this point, at this particular point, this point, then the chopstick tends to fall from the other side. When I try to balance from here, at this point, then the chopstick tends to fall from the other side. Let me find out some point in this chopstick where I can balance this. I am searching for that point. Yeah, I got it. Now I can balance this chopstick over my finger at this particular point. In no other point I can balance this chopstick. What is special with this point? My finger is just below the center of mass of this chopstick. The center of mass. And this point is close to the thicker end and far away from the thinner end. So the center of mass is close to the higher mass end and away from the lower mass end. Now let's consider a system of two masses, m1 and m2. m2 is greater than m1, and the center of mass of these two masses, m1 and m2, is somewhere here in a line connecting m2 and m1. This is the center of mass, this one. The distance of the center of mass from the mass m1 is r1, and the distance of the center of mass from the mass m2 is r2, and the distance from m1 to m2 is r. The center of mass is that point which satisfies the equation m1 r1 is equal to m2 r2, and we know that r is equal to r1 plus r2, therefore r2 is equal to r minus r1. Let me substitute the value of r2 in this equation. m1 r1 is equal to m2 r2 is r minus r1, or m1 r1 is equal to m2 r minus m2 r1, or m1 r1 plus m2 r1 is equal to m2 r, or r1 times m1 plus m2 is equal to m2r. So r1 is equal to m2 divided by m1 plus m2 times r. We have an expression for r1. r1 is equal to m2 divided by m1 plus m2 times r. In a similar way, we can also derive an expression for r2. Therefore, r2 will be equal to m1 divided by m1 plus m2 r. We have an expression for r1 and we have another expression for r2. Now let's consider that there is an axis passing through the center of mass perpendicular to the plane of the two bodies m1 and m2, and about this axis m1 and m2 are rotating. So m1 is rotating through this red circle about the axis which is passing through the center of mass, and the radius of this orbit through which the m1 is rotating is r1. At the same time, m2 is also rotating, and m2 rotates in a circular path with the radius r2. Since these two bodies are rotating, the moment of inertia of the system I is equal to m1 r1 square plus m2 r2 square. Let us substitute the value of r1 and r2 in this equation. I is equal to m1 r1 square. r1 is m2 divided by m1 plus m2 times r. So m2 square divided by m1 plus m2 the whole square times r square plus m2 times r2 square. r2 is m1 divided by m1 plus m2 times r. So m1 square divided by m1 plus m2 whole square times r square. This is equal to, we have the same denominator, m1 plus m2 the whole square. So we get an equation r square times m1 m2 square plus m2 m1 square divided by m1 plus m2 the whole square, or r square times m1 m2 times m1 plus m2 divided by m1 plus m2 whole square. Let us cancel m1 plus m2 and m1 plus m2. Then we get an expression m1 m2 divided by m1 plus m2 times r square. See, this is a two-body problem. Two bodies of mass m1 and m2 rotating each other about an axis passing through its center of mass, and we calculated the moment of inertia of this system. I is equal to m1 m2 divided by m1 plus m2 times r square. For simplicity, a two-body problem can be reduced to a one-body problem. Let's try to do that. This is a one-body problem. This large body is at rest and the small body is rotating around the large body. The axis of rotation is passing through the center of the large body. And the distance from the large body to the smaller body is r. Since only one body is rotating now, it's a one-body problem, and the moment of inertia I is equal to mu r square, where mu is the mass of this small body. If fortunately this mu is happened to be m1 m2 divided by m1 plus m2, where m1 and m2 are the masses we found in the two-body case. If mu is equal to m1 m2 divided by m1 plus m2, then both systems will have the same moment of inertia. In other words, a two-body problem of masses m1 and m2 with both bodies rotating about an axis passing through the center of mass can be reduced to a one-body problem by resting one of the masses and allowing the other mass to rotate with an effective mass mu, which is equal to m1 m2 divided by m1 plus m2, which is called the reduced mass of the two masses m1 and m2. We have simplified the system, a two-body problem to a one-body problem. This is an important concept. We will apply this concept many times in our study of quantum chemistry. And now we will apply this concept for the case of hydrogen atom. In the Bohr model, we considered that the nucleus is at rest and the electron is rotating around the nucleus in circular orbit. But it is not necessary to consider like that. We can also consider that both the nucleus and the electron are rotating each other about an axis like this through the center of mass of the nucleus and the electron. In the case of hydrogen, the nucleus is nothing but the proton. So there is a center of mass between the proton and the electron, and there is an axis through the center of mass, and both proton and electron are rotating about this axis. We can consider like that. Why not? In that case, we can reduce this complicated system, a two-body problem, to a one-body problem, considering that the nucleus is at a rest and the electron is rotating, but not exactly considering the mass of the electron, but by considering the reduced mass of the proton and the electron. We already saw how to reduce a two-body problem to a one-body problem. The same way we can do this. So the reduced mass of the proton and the electron is Me MP divided by Me plus MP. This is the reduced mass of the proton-electron system. Me is the mass of the electron and MP is the mass of the proton. Let's calculate this. Me is 9.1096 times 10 raised to minus 31 kilogram, that is the mass of the electron, times MP, the mass of the proton. Mass of the proton is 1.6726 times 10 raised to minus 27 kilogram divided by Me plus MP, that is 9.1096 times 10 raised to minus 31 kilogram plus 1.6726 times 10 raised to minus 27 kilogram. This is the reduced mass of the proton-electron system. You can calculate this, and the value of this one is 9.1046 times 10 raised to minus 31 kilogram. This is the reduced mass of the electron-proton system. You can see that the exact mass of the electron is 9.1096 times 10 raised to minus 31 kilogram, but the reduced mass of this system is 9.1046 times 10 raised to minus 31 kilogram. These two are two masses which are very close to each other, right? Or the reduced mass of this electron-proton system is equal to 0.9995 times mass of the electron. This is approximately equal to 1. So the mass of the electron and the reduced mass of the electron-proton system are almost equal, or reduced mass of the electron-proton system is approximately equal to mass of the electron. We derived the expressions in Bohr model considering a one-body problem, that the nucleus is at rest and the electron is rotating. We have certain expressions derived from this concept. So we can use the same expressions, but in the place of the mass of the electron, we will substitute the reduced mass of proton-electron system. In that way, we can get the results of this consideration of the rotation of electron and proton around the center of mass. For that, let us derive the expression for the Rydberg constant. Bohr calculated the Rydberg constant with the equation RH is equal to m e raised to 4 divided by 8 epsilon 0 square c h cube. By applying the reduced mass concept, we can substitute the value of the mass of the electron with the reduced mass of the proton-electron system. So the Rydberg constant is equal to mu, that is the reduced mass, e raised to 4 divided by 8 epsilon 0 square c h cube. Mu, we already know what is the value of mu of the proton-electron system, and if we are substituting this value 9.1046 times 10 raised to minus 31 kilogram instead of 9.1096 times 10 raised to minus 31 kilogram, we get a better value for the Rydberg constant, which is equal to 109,681 centimeter inverse. This is a new value of the Rydberg constant calculated using the reduced mass concept. And we know that the value of the Rydberg constant calculated from the simple Bohr model using the mass of the electron alone was 109,737 centimeter inverse. This was the value calculated from the simple Bohr model. And we know that the experimental value of Rydberg constant is 109,677 centimeter inverse. Now let's compare these values. This is experimental value based on the simple Bohr model, value based on the reduced mass concept in Bohr model. Which value is closer? The value obtained by substituting the reduced mass of the proton-electron system gives a much better value than the simple Bohr theory, which considers only the mass of the electron. So the reduced mass concept has led to even much better value for the Rydberg constant. So this method of considering the reduced mass of the proton-electron system, or by considering the rotation of the proton and electron about its center of mass, will give better spectral values. In this way, the Bohr model can be refined. Are you confused of thinking that what a complicated system is this? Both nucleus and electron, both are rotating. How is it possible? It is not so much complicated actually. We only saw that R2 is equal to M1 divided by M1 plus M2 times R. We already derived this expression. In the case of the proton-electron system, the distance of the center of mass from the proton or from the nucleus of the hydrogen atom, that is Rp, is equal to Me divided by Mp plus Me times R. That is equal to 9.1096 times 10 raised to minus 31 kilogram divided by 1.6726 times 10 raised to minus 27 kilogram plus 9.1096 times 10 raised to minus 31 times R. R is the distance between the nucleus and the electron. And this is something of the order 10 raised to minus 4 times R. Or it is like R divided by 10,000. See, the center of mass is very, very close to the proton. This is R divided by 10,000. So the center of mass is not somewhere here, far away from the nucleus. It is almost in the nucleus, because the mass of the proton is very, very large compared to the mass of the electron. So the center of mass is very close here. So the rotation about this center of mass is something like, you won't feel the rotation of the nucleus in this approximation also. You won't feel the rotation. Hydrogen is a one electron system, and Bohr theory was very much successful to explain the spectral features of hydrogen. And this Bohr theory can be extended to other one electron systems also, like helium plus is a one electron system, and lithium 2 plus, this is also a one electron system. And you can derive the expressions for these ions. But only thing you have to consider is that here in this case, the charge of the nucleus is Ze, where Ze is the atomic number. In the case of hydrogen, Z is equal to 1. In the case of helium, it is 2, and in the case of lithium, it is 3. And we can derive the expressions for the spectral lines using the nuclear charge of Zd for any one electron system. In general, nu bar, the wave number, is equal to z square mu e raised to 4 divided by 8 epsilon 0 square c h cube times 1 by n1 square minus 1 divided by n2 square, where n2 is greater than n1. This is the expression for the wave numbers for the spectral lines for the one electron systems. Here, for deriving this expression, we only consider that the mass of the charge of the nucleus is Zt. So we have found that the Bohr model was very much successful to explain the spectral lines of the emission spectrum of the hydrogen by giving a theoretical explanation for the Rydberg formula. And it was possible to extend this to other one electron systems also. And one of the biggest success of the Bohr theory was that it could explain certain lines in the solar spectrum that scientists were clueless about the origin of these lines. For example, the Pickering series in the solar spectrum. Pickering series are the series of lines at the wavelength 4551 angstrom, 5411 angstrom and 10123 angstrom. Initially, scientists were thinking that this may be coming from hydrogen, but at the same time, Rydberg formula was not able to account for these lines. Rydberg formula was able to account for a whole series of lines in the hydrogen spectrum, but these were assumptions. These were found to be anomalous. And after the introduction of the Bohr theory, the scientists could assume that this is not from hydrogen but from the helium plus. These lines occur from the transitions from 9 to 4, then 7 to 4 and 5 to 4 energy levels in the helium plus. Some transitions are missing. For example, 8 to 4 transition is missing and 6 to 4 transition is missing. It is not just missing, actually it is overlapping with the hydrogen spectrum. So these three lines are generally considered as Pickering series, and scientists were able to find out the origin of the Pickering series. It is not from hydrogen but from helium plus. And this was a very big success of the Bohr model. But Bohr model faced failures also. One of the biggest failures of Bohr model was that it could not be extended to multi-electron systems. We already found that it could explain the spectral lines of the single electron systems, but it could not be, unfortunately, extended to the multi-electron systems. This was a big failure. And another thing, we know that when an atom is subjected to magnetic field, the spectral lines will split into individual components, and this is called the Zeeman effect. Bohr model was not able to explain this phenomenon. And thirdly, Bohr model was not able to explain the intensities of spectral lines. It was able to explain the positions of the spectral lines in the case of single electron systems, but it failed to explain the intensities. So, Bohr model was a good beginning. It showed that by bringing quantum theory, a stable model of atom can be created, at least for the one electron system. But at the same time, even for the one electron systems, it failed to explain certain important phenomena. It says that even if Bohr model was very much successful, even if the concept of quantum theory applying to the atomic and subatomic systems are very much promising, the Bohr model was not everything regarding the structure of the atoms. So some new models are to be developed, new theories are to be developed, that we will learn in the remaining classes.